The purpose of this video is to review some things that we already know about exponential functions. Remember that exponential functions are functions that look like the examples I'm about to write down. So we could have something like y equals 2 to the x, or we could have something like y equals 3 times 4 to the x. These are examples of exponential functions. The number underneath the x is called the base, and the x is a power. So for an exponential function, these are things that have to be a part of our function. So here are two examples of exponential functions. If you notice, just like we just said, we have a power, and the power is a variable. It's our x. We have a base, and that's what we have right underneath that power. But we have some other things that we want to identify. These things are going to give us attributes such as the vertical asymptote, if we have one, horizontal asymptote, if we have one, and so forth. So why don't we take a look at how these particular attributes would tell us what these quantities would be. So now let's take a look at how the values that we could have within an exponential function would help us to determine what its attributes are. So what we've discussed previously was that the constant, this value here, d, would tell us what our horizontal asymptote is. So whatever that number is, that's going to be our horizontal asymptote. The horizontal asymptote of an exponential function is always linked to the range. So that value d, whatever that number is, that's going to start the range off. So the range in this case is going to go from d to infinity. The domain, well, we'll revisit the domain at the end. Why don't we look at the vertical asymptote? The interesting thing with exponential functions, and the easiest thing with exponential functions, is that the vertical asymptote will never exist. In other words, if we have an exponential function, the vertical asymptote will always be none. Now, if we were to find the y-intercept, how would we do that? Notice that for the y-intercept, that we're going to make x equal to 0. Let's say that we did that within this problem. Y equals a times b, and then we have c times x, but we're making the x 0 plus d. What's c times 0? 0. So we're going to have y equals a times b to the 0 plus d. Any number or any value to the 0 power, what does that give you? That gives you 1. So we're going to have y equals a times, and remember, b to the 0 we just said is 1. Anything to the 0 power is 1 plus d. Remember, all of the work that we're doing here is to find out the y-intercept. So when we finish this, we're again going to end up with the y-intercept. So a times 1 is a. So we're going to end up with basically a plus d. So the fast way to work this out basically is if we know what a is and we know what d is, we're going to just go ahead and add them together to get our y-intercept. So our y-intercept again is going to be 0 comma whatever a plus d is going to give us. Our x-intercept, how would we find that? Well, we'd have to make the y 0. This is not always possible. And really the only time we're going to have an x-intercept for the average exponential function is if we have a negative asymptote. So this is really conditional. This is really only going to happen if we have a negative asymptote. So finally, let's talk about the domain. We don't need to look at any of the numbers to find the domain because there are two possibilities in terms of how the graph can look. either we have exponential growth or we have exponential decay. In other words, it's either increasing or decreasing. Let's look at the graphs. If it's increasing, notice that the graph basically is going to continue always to the left and always to the right. So in other words, we're always going towards negative infinity in one direction and positive infinity in the other direction. Same thing if it's decreasing. It's either always going to the left or always going to the right. So one side is going to negative infinity, the other side is going to positive infinity. So what would our domain be? No matter which way you look at it, for an exponential function, the domain would be from negative infinity to positive infinity. So let's apply that same knowledge to this specific problem. Suppose that we had to find the horizontal asymptote. What would you do? Remember that to find the horizontal asymptote, we need to look at the constant value, in this case, the 30. And we call 30 the constant because it does not have an x, it does not have any variable associated with it. So our horizontal asymptote would just be y equals 30. What would our range be? Remember that we're using the same number to find the range. So our range would start at 30 and would continue to infinity. So how would we find, let's say, the y-intercept? We could set x equal to 0 and work it out, but remember, the fast way, the simplest way, is just to take the constant and our value here and just work out the problem that we have. So in this case, 50 plus 30 is going to give us 80. So that means that our y-intercept is 0, 80. What about our x-intercept? We're only going to have our x-intercept if the horizontal asymptote is negative. So in this case, it's a positive horizontal asymptote. Remember, we got 30. So we're going to say that there is none in this case. So what about our last two attributes, the domain and our vertical asymptote? Well, remember, this is an exponential function, so there is no vertical asymptote. And also, our domain, remember, we're either increasing or decreasing. And because the base is greater than 1 here, we're saying that it's increasing. So our graph is going to look something like what we have here on the left. But in any case, whether it's the graph on the left or the graph on the right, what we said was that it's always going towards the left and it's always going towards the right. So our domain would be from negative infinity to positive infinity. If we change this function, what would happen? How would the graph change? Well, remember that the function we just looked at said y equals 30 plus 50 times 3 to the positive 1/5 x. When we graphed it, we had an increase. So how does changing the x to the opposite, how does that affect a graph? So well, let's just think about points in general. If I have a point, let's say I have a point 3, 5, just some random point, and I said, let's make the x value become the opposite. So now it's negative 3, 5. And we said, let's graph it. What would happen? Well, we'd have to go left and up to graph that point. So that's where negative 3, 5 would be. So whenever we go from a positive x to a negative x, what happens is that we flip or we reflect across y. So if we took that same graph, the original graph we just had, and we flipped it across the y, what would happen? Well, this point would end up here, 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 these points would end up here, and if we kept going, what we'd end up with is a graph that looks like that. So whereas the original function with a positive x value, when we had y equals 30 plus 50 times 3 to the positive 1/5 x, so positive x, whereas that one, when we graphed it, was an increase. When we change it to a negative x, what that's going to do is that's going to cause it to decrease. So how does that affect our attributes? Well, it's still going always to the left and always to the right, so our domain would still be from negative infinity to positive infinity. Our horizontal asymptote didn't change because we still have the same barrier right below each function, so we would still have a horizontal asymptote of 30. Because it's still an exponential function, we still would not have a vertical asymptote. Our y-intercept wouldn't change because if we flip a point that's already on y across the y, it's the same point, so it's still 0, 80. We still wouldn't have an x-intercept because of where our horizontal asymptote is. And our range would be exactly the same. We would still go from positive 30 to infinity. So let's revisit this function that we looked at earlier. What if there were some restrictions? What if this function represented the amount of money that we made over time? In other words, let's say x represented time and y represented the amount of money that we made. What would it look like and how would we interpret the attributes? Remember that these are the attributes that we got, but how would it look if we said that y represented the amount of money that we made, and let's say that x represented the time that was put into making that money? Well, let's first graph our results. So here's our graph. If you notice, again, we said that y represented the amount of money. So this axis would be money, and x represents the time that it took. So we would put the time that it took down here. Of course, we can't have negative time, so that's the reason why we have dotted lines over here. And we would prefer not to have negative money, so we're going to leave this section off of our graph also. But that's basically what the graph would look like. I included a section here that indicates what the graph would look like if that portion of the graph were available. But in any case, how do we actually interpret this? Well, we know our y-intercept was 0, 80. So what that means is that when we started at time 0, that the money that we started with was $80. So we started with $80. One other thing that we want to notice about this scenario is that the domain no longer makes sense, because if you notice, our domain started at negative infinity, but the negative infinity portion of our graph does not exist. So where does everything start? It starts at 0. So if we rewrote everything, we would say that we're including 0, that's where it's going to start, and it's going to continue to infinity. The range would also be different in this real life scenario, because as opposed to the smallest value here being 30, because our graph is going to continue towards the asymptote, we're starting at 0. So what that means is that, again, 30 would have been our asymptote, but we're not going to get anywhere near that. We're starting at 0. So our actual range in this problem would be from 80, because that's the smallest y value that we have, continuing on to infinity. So just to reiterate that point, the smallest y value that we have, is at 80. So that's the smallest place that we're going to be at. Before, we would be at or close to 30 because we have an asymptote. So in this case, because again, a real life scenario and we don't have negative time, we're starting at this point. That means 80 is the lowest number that we're going to have. So what that means is that we will never, so this implies that we will never have less than $80.